Hello everyone, I'm Mr. Cobalt, and in this video I'm going to go over another practice problem involving the figuring out of the enthalpy of a reaction in a coffee cup calorimeter. So again, this is going to be a constant pressure calorimetry. And so in this second problem, we have another reaction where you have silver nitrate aqueous reacting with hydrochloric acid, and that's going to form silver chloride solid. So we have a precipitate plus uh, nitric acid. And so what we're being given here is that we mix 50 milliliters of a 0.100 molar hydrochloric acid with 50 milliliters of 0.11 molar silver nitrate. So basically what you're going to be doing is you might have the hydrochloric acid in the coffee cup calorimeter already, and maybe you have a graduated cylinder of the silver nitrate, and then at some point when you're ready, you're going to pour in the silver nitrate, and then you're going to measure the temperature and then measure the reaction as it's going by measuring the temperature. So, so you're going to have the initial temperatures of both solutions, which should be the same for each solution. And then when you mix them together in the coffee cup calorimeter, you cover it and then you mix it, and then you're measuring the change in the temperature, and then you measure the maximum temperature change. So the maximum temperature, whatever that is, that's going to be your final temperature. And then again, that's going to be the final temperature of the solution. Okay, so so we're given this, and we're also given the initial temperature, we're given the final temperature, and we're given the density and the specific heat of the solution. And again, you'll notice that the density of the solution is given as 1.00, which is the density of water, and the specific heat of the solution is given as 4.18 joules per gram per degree Celsius, which is also the specific heat of water. So we're assuming that that this is basically like water, that the solution is like water. That's not always going to be the case, but in these problems, that's what we're assuming. All right, so again, we're looking for the delta H of the reaction. So the way you're going to set this up again is you always set everything up to 0. So 0 is going to be your Q1 plus your Q2 plus whatever else is involved. But in this particular reaction, the only two things that are involved is the reaction itself, with it, which is your system, and then you have your surroundings. And the only surroundings that are going to be absorbing the energy or giving energy to the reaction is going to be the solution. In a coffee cup calorimetry problem, we're assuming that no energy is absorbed by the styrofoam cup. And so this is going to be equal to, once again, Q1 we'll say is Q of the reaction plus Q2 is going to be the Q of the solution. And then once again, that's going to be Q of the reaction. And then the Q of the solution, once again, is going to be Q of the solution is equal to the mass of the solution multiplied by the specific heat of the solution, and then multiplied by the change in temperature. So change in temperature, again, is going to be final minus initial. So if we put that in for the for the Q of the solution here, this will then be plus mass of the solution multiplied by the specific heat of the solution multiplied by the final temperature minus the initial temperature. Okay, so now that we have that, so we're going to have 0 is equal to, and then we can plug in the values that we have. So we need to find the mass of the solution. So we're given, now the one thing you want to watch out for is limiting reagent problems. So notice that they just gave me a volume and concentration of one reactant, a volume and concentration of the other reactant. They didn't say anything about the reaction reacting to completion. So you need to make sure that this is not a limiting reagent problem. Now, normally you would just figure out the number of moles and see if there's the balance of the moles, right? So you could multiply the volume in liters times the molarity and the volume in liters times the molarity and see if the ratio is the same, or you can convert both of those to a certain amount of product given your reaction and see which one gives you the lesser amount of product. But in this case, you can see that in the reaction here, the reactants are 1-to-1. And you'll notice that the volumes here are the same and the molarities here are the same. So the number of moles you get from each of these is the same. So these are the same moles, 1-to-1, and this is 1-to-1. So it is not a limiting reagent. It's going to react to completion. Okay, that's good. So we need to figure out the mass of the solution. So we're given 50 milliliters of one, 50 milliliters of the other reactant. Add those together, we get 100 milliliters, and we're told that the density of the solution is 1.00. So that means the mass is going to be it's going to be 100 milliliters. So we got a total of 100 milliliters of our solution. We can use the density as a conversion factor. So again, 1 milliliter over 1 or under 1.00 grams of the solution. That's going to cancel out, and then we end up with 100 grams of the solution. So this is going to be Q of the reaction plus 100 grams. And then the specific heat of the solution is 4.18. So we're going to do 4.18 joules per gram degrees Celsius. And then multiplied by the change in temperature. So the initial final temperature minus initial final is 24. So we have 24.21 degrees Celsius minus the initial 23.40 degrees Celsius. Okay, so now all we need to do is calculate that amount. So I have my calculator here. So we're going to multiply 100 times 4.18 times, and it's going to be 24.21 minus 23.40 equals. And so that's going to give us, so 0 is equal to Q of the reaction plus 338.58 joules. And so we know it's joules because grams cancels out, the degrees Celsius cancel out, so we're left with joules. Now we have to pay attention to sig figs. So we have 24, so if we subtract, remember when you're subtracting, you're looking at least number of decimal places. So your answer should here be the least number is 2 each. So this is 2, this is 2. So your answer here should be in 2 decimal places. So if I do 24.21 minus 23.40 equals, that's going to be 0.81. So I get 0.81 degrees Celsius. So there's my 2 decimal places, but notice it is 2 sig figs. So when I multiply these together, so I have two sig figs here, I have 3 here, 3 here, and so that's going to be 2. So this final answer is going to have to be in 2 sig figs. So I'm going to mark that there so I can remember that I only have 2 sig figs for this particular calculation. Okay, so now that I have this, The positive number again here is for the solution. That tells me that the solution gained energy. So it's positive for the solution. If the solution gained energy, then the reaction gave energy to the solution. So that means that this reaction has a negative heat. So it's an exothermic reaction. So we can see that by bringing this over. So Q of the reaction is equal to negative 338.58 joules. And again, if we convert that to kilojoules, it's going to be 0.33858 kilojoules of energy, because we divided by 1,000 to get that. And so again, this 3 is the last significant digit. That 3 there is the last significant digit. So now we have the Q of the, oops, this should be negative. So the heat of the reaction is negative 0.338, but that's for the whole reaction. Okay, so what we need to figure out is also the number of moles that was reacted. So they gave us 50 milliliters of 0.100 moles per liter of hydrochloric acid. They also gave us the other one as well, the other reactant. So if we want this per mole of reactant, then we need to figure out the moles of the reactant. So here we take the 50 milliliters of, we'll take HCl. So milliliters of HCl over 1. We're going to convert that to liters. So we have so 1 milliliter is 10 to the negative 3 liters. So milliliters cancels out. Now we have liters. Now we can use molarity as a conversion factor, and that's going to end up being moles over liters. So 0.100 moles of HCl over 1 liter of HCl solution. Liters cancels out, milliliters cancels out, and we can calculate this. So it's going to be 50 multiplied by 10 to the negative 3 multiplied by 0.100 equals, and we get moles 0.005 moles of HCl. And so that's the number of moles. Now we can take this and divide it by, so we got negative 33858 kilojoules. We're going to divide that by the number of moles we have, 0.005 moles of HCl. Oops, should be HCl. And so we have 0.33858 divided by 0.005 equals, let's do that again. So we're going to get 0.33858 divided by 0.005 equals, and we get negative 67.716 kilojoules per mole. But remember, we only allowed 2 sig figs, so this is going to be negative 68 kilojoules per mole. And so this is, again, an exothermic reaction because it's negative, so that's what we would have expected. Thank you for joining me, and